This webcast continues the discussion of the lab activity on energy stored in a spring. And I'm now at step 15, which asks us to create a graph of the stored elastic potential energy versus the displacement of the end of the spring. So if I go and look at my data, now I want the elastic potential energy in the spring to be on my y-axis, and I want, let me go back and make sure that I know what I want. And I want the displacement of the end of the spring to be the x-axis. And so that's what I have labeled as x. Okay, so I'm going to graph this column versus this column. Now these two columns are not adjacent to each other in my spreadsheet. Let me show you. So I could just copy these and put them next to each other and then do a graph the way you're used to doing it. But let me show you another way. So I'm going to highlight the x values, okay, the numbers in this column, and then I'm going to hold down the control key and keep holding down the control key while you select the values in the other column. Okay, so since I held the control key down, I was able to select these two columns that are not adjacent to each other. And then I'm going to go and insert a scatter plot. Okay, I'm just going to shift it to the right. Okay, so this is the graph. Wow, look at the curve on that. Once again, I have the issue that the labels on the vertical axis are in the middle of my graph. And so I'm just going to do a right click on one of those numbers, go to Format the Axis, and then if you slide down here and open up the options for labels, I can tell it to put it at the low position. That just moves that to the left. It makes this graph more legible. Okay, oh dear. I don't know, I wish it wouldn't open this thing. Okay, here we go. So, interesting graph. Let me put some axis labels. So here I have the displacement of the end of the spring in meters, and over here I have the elastic potential energy stored in the spring, and that's in joules. Okay, and so the title above the graph should say elastic potential energy stored in spring versus displacement of the end of the spring. Okay, quite a mouthful. Okay, we probably want to copy this graph, and let's put it into our report at figure 2. Okay, so that is the stored elastic potential energy versus the displacement. Okay, so now it's going to ask me what kind of relationship we have here. So if you look at that graph, it's shaped like a parabola, right? I mean, we can really see the shape of this as like a parabola. So I'm going to say here, the graph of elastic potential energy stored in the spring versus the displacement of the spring is curved and resembles a parabola. Therefore, the elastic potential energy is proportional to the square of the displacement. Right? A parabola has the shape, or has the apparent equation, y equal, some slope times the square of x. Our x variable in this graph was the the displacement of the end of the spring, and our y variable was elastic potential energy, so that means that elastic potential energy is proportional to the square of the displacement. Okay, now it wants us to transform the data to create a linear graph, right? That we do that so that we can make a physics equation. When we do this, we're going to have to attach both the table and the graph, okay, in our report. Okay, so let's see here. I'm going to go back to Excel, and the original data table is right here. I'm going to copy these two columns. Let's see, I'm just going to highlight it and say Control-C, and let's just go down a little bit and paste it. That's the displacement of the end of the spring. And then up here, I'm also going to copy the column for the elastic potential energy, right? Those are the two things that we graphed to get that curved graph. Okay, so in order to make this linear, I need to transform and make this not the displacement of the end of the spring, but the square of the displacement of the end of the spring. It's going to be delta x squared. Okay, I'm not going to do anything to the elastic potential energy. Now, you could copy these. I'm sorry, not copy them, but you could calculate the square yourself. But I'm going to show you how to put in a formula in Excel. Since it's a formula where we want Excel to calculate something, you have to begin with an equal sign. So I put an equal sign, and then I scroll up until I see the table above, and I'm going to click in the cell for the first value of displacement. Okay, so now my formula is working here. Right now I have that equals the value that's in cell A6. For me, that's A6. Do a Shift 6 key up here to get that little caret sign, and then type a 2, because we want to raise it to the power of 2. And then you can hit the Enter key. Okay, so now it says the square of the displacement for this first value is 1. Okay, 1 squared is 1, so maybe we're not 100% sure, but if you just copy this down, I think you'll see that it has successfully taken the square of all of your displacements. Okay? Once you've done this, then you just need to do this graph. So I'm going to highlight these numbers and insert a scatter plot. And look, it's beautifully linear. That's what we were trying to do. Let's put some axis titles on it. Now on the x-axis, it's no longer the displacement. It's the square of the displacement of the end of the spring. So now this is in meters squared, not just meters. Oh, I should have fixed this over here too in my header. This is now meters squared, okay, because it's the square of the displacement. And then on my vertical axis, I still have the elastic potential energy in joules, okay? And my chart title is elastic potential energy versus the square of the displacement of the end of the spring. Okay, so I want, let me just adjust the location here. I might just make it a little bigger. I'm going to copy all of this, the table and the graph. Do a Control-C, and then I'm going to paste it in my report under Figure 3. And there we go. So I have the data table and I have the graph. So you need to put both of them in your report here. Okay, so give the value of the slope, including the units. Okay, so let's see. So every one of these data points is on this graph, and so I'm just going to calculate the slope by hand, choosing 2 of my data points. Let's see here. I can see 2 right now. Let's see. So I'll just say 200 minus 0, and that's joules, over 1 minus 0 meters squared. So I get a slope of 200 joules per meter squared. Okay, so I've shown how I calculated my slope. So what would the physics equation be? My independent variable is the square of the displacement. And so I'm going to use a symbol for that, which is delta x, that's displacement, squared. The dependent variable is the elastic potential energy. Which I'm just going to call EL. And so my physics equation would be EL equals my slope, which is 200 joules per meter squared, times delta x squared. So the slope in this figure is related to the value of spring constant that you chose at the beginning. How is it related? Well, for me, the slope equals 1/2 of the spring constant. That is the relationship I see. My slope here is 200, but my spring constant was 400. That was the thing that I chose at the beginning of the lab. So now it says rewrite the physics equation, replacing the numerical value of the slope with the meaning. Okay, so my physics equation was EEL equals some slope times the displacement squared. But the slope is 1/2 of the spring constant, K. And it says this version of the physics equation is the definition of how to calculate the elastic potential energy stored in a spring. It's 1/2 the spring constant times the displacement of the spring squared. Okay, so then we get to our final conclusions here, and we'll just quickly go through those. Elastic potential energy is energy restored as a result of the deformation of an elastic object, right? Deformation means that you change the shape. According to Hooke's law, the force required to either compress or stretch a spring is proportional to the displacement of the end of the spring. And this was demonstrated in Figure 1, where the relationship between the force applied to the spring and the displacement of the end of the spring was found to be linear. And then I'm going to leave it to you to copy down your physics equation here, right? Where we had the applied force equals some slope multiplied by the displacement of the end of the spring. Don't forget to put the value of your slope. And then we've answered these questions up above, so you can find that. But let's go on to the last paragraph here. The amount of elastic potential energy stored in the spring, it increases as the deformation of the spring increases. The stored elastic potential energy is proportional not to the displacement of the spring, right? That EL versus displacement was curved, but is proportional to the square of the displacement of the end of the spring. And so I'll let you also copy that physics equation down. We had the elastic potential energy equals some slope times the square of the displacement. Okay, and then the last part of this lab are some application questions. So the first thing you're going to do is to find the spring constant. It gives you this new set of data. Remember, the spring constant is the slope, but remember that that this data is given to you in newtons per centimeter. So you're going to calculate the slope, right? y2 minus y1 over x2 minus x1, but that's going to be in newtons per centimeter. And so you're going to have to multiply by the number of centimeters that are in 1 meter in order to get your answer in newtons per meter, because that's what you need to do. Okay, then you'll explain the meaning of the spring constant. Remember, it's a slope, so you're going to do for every additional, this is very much like what we did earlier in the lab. For every additional 1 meter that the end of the spring is displaced, you're going to explain what happens to the applied force. And here you're actually going to calculate the applied force, right? Applied force equals that spring constant times the displacement, but be sure to convert to meters before you plug in this amount. Okay, and then how much elastic potential energy, this is energy, not force, would the spring store? That's going to be 1/2 of the spring constant times the displacement squared. And again, you need to be sure to convert to meters, from 28 centimeters into meters. Okay, we've finished this lab.